All right, folks. So here is a solid sphere of some unknown mass of radius r is equal to 0.3 meters. It is going to be rolling down the ramp without slipping. So aka it's going to be moving linearly and also spinning at the same time. The length of the ramp, which is given to us here in the statement, is 9 meters, and the angle of the ramp is 30 degrees. Okay. So part A, B, and C. If you want, pause the video and take a second, write it down, or read it for yourself. Part A asks us to find the angular speed at the bottom. Part B asks us to find the time, and then part C just has to prove that ACM is given by 5/7 g sine theta. All right, so I'll go ahead and do part A. So part A, you first recognize that you need to use conservation energy. Conservation energy because the sphere initially starts off a height above the ground, so it has to have P due to gravity, and then as it rolls down, it has a KE linear and also a KE rod because it has two motions, KE linear and also KE rotational. Okay. All right, so we can expand PE grav, which is mgh, and then that's going to equal to 1 half mv squared plus 1 half I omega squared. But the moment of inertia for a solid sphere, I went ahead and just skipped a line here, which is 2/5 mr squared. And then as you see here, the m appears in every term, so that'll cancel out. And then in the second term on the right side of the equal sign, the 2/5 has the 2 in the numerator, and then the 1 half in front part of the function has the 2. So that's going to cancel out. So I'm going to clean this up a little bit. So in the next line, this is what I have carried down. But what you do notice here is that you have a VF and an omega F. But part A asks you to find omega, not VF. So to get rid of VF, we can just do a quick substitution. V is simply R omega. In this case, since it's VF, I replace it with R omega F. And that square for the VF square is outside the parentheses. So do not forget to distribute this square to the R inside and also to the omega F inside. And when you do that, you get two terms on the right side that are the same because this is r squared omega f squared. When you distribute the square, it'll be also be r squared omega f squared. And then to find common denominator, here's the 2, here's the 5. Common denominator is 10. So you multiply the 2 by 5 on the bottom, that makes 10. Multiply the top by 5, so that's 5 on the top. Over here, we have 5 times 2, which is 10. And then we have 1 times 2, which is 2. So we add the numerator, which is 5, plus 2, which is 7. And then the common denominator is just 10. So that's where the 7/10 r square omega f square comes from. All right. So here, to solve for omega f square, we can go ahead and just multiply both sides by 10, divide both sides by 7, and also divide both sides by r square, which is what I have on the left side of the equal sign here. And then from there, we just have to recognize that everything's given to us except for h, but that's okay. Let's do a little geometry. Sine of theta is equal to opposite, which is h, over hypotenuse, which is x. So that's what I have here. Sine is equal to opposite, which in this diagram is called h. The hypotenuse, which is called x. So I need to find h because that's what I'm missing in this statement that I have set up here. So to find h, multiply both sides by x, and therefore we know that h is equal to x times sine of theta. From there, we can just do a quick substitution. So wherever h is, we can just plug in x sine theta. And as you hopefully see by now, we know what g is. G is 9.8, x is 9, sine of theta is 30 degrees, and r is given to us as 0.3. Don't forget to square that. So if you do a little plug and chuck in your calculator and then square root that, you should get a value of 26.46 radians per second. So that's your final speed. I don't care for the direction here because it asks for speed. Okay. All right, let's do part B. I'll show you how to do part B using multiple strategies, and hopefully you like one or two of it and then stick with it. All right, it asks us to determine the amount of time. So in no particular order. The first one I have here is using rotational motion, rotational kinematics. Omega average is equal to angular displacement over time, but we also know that the omega average is also omega f plus omega I divided by 2. We have two functions that are the same. We can set them equal. From here, you have to recognize that you're trying to find time, so I went ahead and flipped the function upside down. Delta t is in the denominator. To get it to the top, I'm going to flip the whole entire function, not just the left side, upside down, so that I can get t by itself on the top. And then to get t by itself, I need to get rid of this angular displacement. So I would have to multiply both sides by delta theta. So it's going to look like this. All right, so from here, we know that omega f from part A is 26.46. We know omega I is 0 because it starts at rest. So the only thing holding us back here is the angular displacement. But this strategy that I have here just uses your prior math knowledge. You hopefully by now know that the circumference of a circle is just 2 pi r. That is the linear length that it traces out when it completes one revolution, aka a circumference. Okay. All right, so the circumference of the circle or the sphere in this case would just be 2 pi. The radius given is zero point 0.3, so that'll be 1.885 meters. Now, what do you do with this? You know that the number of revolution is just the length that's covered divided by the circumference of a circle. So each time it rotates, it covers a linear distance of 1.885, but the length of the ramp is a whole entire 9 meters. So by simply taking 9 divided by 1.885, I should get the number of revolutions that's covered by the sphere as it rolls down the ramp. So if you do this basic math, you'll get that it rolls about 4.775 revolutions. Okay. But keep in mind that angular displacement here is in units of rads, not revs. So you have to take this one extra step. So you have to convert 4.775 rev to rads simply by converting it. For every one revolution, there's 2 pi rad. So if you do that, you should get about 30 rad. So we can just substitute 30 rad in for angular displacement. Here we have proper units because the angular velocity here is in rads per second. So again, you cannot just plug in 4.775 revs. You need this to be in units of rad because angular velocity is rad per second. So rad here will cancel out, leave us with just unit of time, which is 2.27 seconds. All right, the second strategy is using your old school kinematics. Average acceleration is just change in velocity over change in time. Break delta v up to vf minus vi. And then to solve for t, swap the delta t and the a average by doing a little bit of algebra there. Okay. But here, we don't know what vf is, but we can find that quickly. We know what vi is, vi is 0. So to find vf, we already know omega from part A, and we know the relationship between that omega and v is simply v equals r omega. So here, r is given as 0.3. We found omega r radius 26.46 in the previous part A. And then from here, we know that at the very, very bottom of the ramp, VCM in this case is going to be about 7.94 meters per second. And then we can just use that information in this particular function on the right that I have set up. So VF would now just be 7.94 minus 0. And then here we're stuck with A. We don't know what A is, but that's okay. Use common form. To find A, we can use VF squared minus VI squared equals 2A delta X. We know VI is 0. We know VF here is 7.94. And then we know delta X is 9. So really the only thing we have that's unknown is A. So manipulate the function by dividing both sides by 2 delta X to get A by itself. Here we just plug and check. Okay, VI is 0. VF again 7.94 we just found. And then X is just 9. If you do that properly in your calculator, you should get 3.5 meters per second square. And then you would just substitute that in there. And then doing that calculator work should give you the same answer of 2.27 seconds. All right, the next one is simply by using the average velocity function linearly, which is just angular displacement, linear displacement over time, which is the same as VF plus VI divided by 2. Again, I'll go ahead and flip the function upside down because I'm trying to solve for t. To get t by itself, I'm going to multiply both sides by delta x. That leaves me with that. I know delta x is 9. I know VF is 7.94, simply converting angular speed into linear speed. All right. And then just plug and check. 2 times 9. VF is 7.94. VI is 0. If you do that, you'll get the same answer of 2.27. The next approach is a little harder, but it's good practice if you want to learn torque. All right. To find time, we can exercise angular acceleration, which is equal to the change in angular velocity over change in time. Again, I'll flip-flop the delta t here with angular acceleration. Again, I broke up delta omega f minus omega I, so that's just get down there. All right. We already know omega f from part A, which is 26.46. Omega I is 0. Here we don't know what angular acceleration is, but that's okay. We just set up torque real quick to find angular acceleration. When I do torque, I like to shift my pivot from the center of mass to the point of contact along the surface. By doing that, I need to use the parallaxis theorem, but it's just a little quicker for me. So I'll pick this as my pivot where I'm pointing on the diagram. I choose my pivot to be the point of contact. By doing that, I've shifted the axis of rotation from the center of mass to the point of contact. So therefore, I need to use parallax theorem. Okay, and then I need to figure out what is the force of force component that is causing that rotation. In this case, if my pivot is there, I have my arm here, which I'm tracing out my cursor. So that is the distance r, and then this f of g sine theta is perpendicular to that r, aka perpendicular to the pivot. So I'll do that. All right, so if I set up torque, the force that is perpendicular to r in this case is f of g sine theta or f of g x. And then here, it's important that you note here that I'd use I knew. Again, I'm not using the moment of inertia relative to the center of mass. I'm using the moment of inertia where it touches the surface incline. So use parallax theorem. If you use parallax theorem properly, here I have f perpendicular r carried down. I divided both sides by I knew, but I knew is just ICM, which is 2/5 mr squared plus m, and the distance shifted is just a distance of r. So it was at the center, and then I shift that pivot to the surface, which is just a distance of r. So this is where the mr squared comes from. All right, so if you do 2 over 5 mr squared plus mr squared, that gives you with a fraction of 7 over 5 mr squared. And then I went ahead and substituted in f here as f of gx, which is f of g sine theta, but f of g is just mg sine theta. So that's where the mg sine theta comes from. And then the r is part of the function, which I carry down there. All right, so hopefully by this point, you know there's an r on top and there's an r square on the bottom. So that's gonna cancel out, and there's also the m will also cancel out. And then that leaves us with this particular function. Here is just g sine theta over 705r, but we know what g is. G is 9.8, theta is 30, r is 0.3. So if you plug it into your calculator, you should get an angular acceleration of 11.67 rads per second squared. And then plug it in to what we're missing over here. And then from there, we just do calculator work, and you should get the same value, 2.27 seconds. Okay. Again, the strategy is a little harder, but it is good practice because it forces you to shift one pivot to apply parallax theorem. Okay, so a little tedious, but it's good practice. All right, here I have angular acceleration. Again, it's omega f minus omega I divided by change in time. Omega f, we already know from the previous answer. Let's solve for t. We'll flip flop a little bit here, do the same algebra manipulation as the previous strategy. Omega I is 0. But you notice here, we know omega f, but we don't know angular acceleration. Okay. But instead of shifting my pivot, I'll show you how to do it using the pivot at the center of mass. So in the diagram, there's my pivot, aka the center of mass is where the arrow is pointing to. So if I use this as my pivot, I have to figure out what force is causing this rotation. The force that's causing this object, solid sphere, to rotate is the force of friction where my cursor is. Okay, and that force of friction is the distance of r away, which is perpendicular to the pivot. All right, so there it is. It comes up on the screen. And I also have FGX as well. But you notice here, if you're going to use this reference point center of mass, you do not want to use f of g sine theta because f of g sine theta runs through the pivot, which will generate no torque. Okay, so the strategy uses the pivot at the center of mass. And if you do that, you have to use the force of friction because the force of friction is the distance of r away from the pivot, which will generate torque. In this case, it's going to roll spin clockwise. All right. So we're kind of stuck with the same here. We know omega, but we don't know alpha. So to find alpha using this strategy, it's a little tedious, but again, it's good practice. We have the force of friction times r because in this strategy, the force of friction is what's causing the torque. Here I have I highlighted. I, because we didn't shift the pivot runs through the center of mass. It is just simply 2/5 mr squared. So do not apply parallax theorem here because I'm using the center of mass as my pivot. So everything stays quote unquote normal. Okay. All right. From here, we don't know what f of fric is. We know what r is, and we're trying to find alpha because in the statement down here, we know omega f, we know omega I. The only thing missing is angular acceleration. If we don't know what f of friction is, we can go find it by setting up Newton's second law. So in this particular function, if you do just look at the linear stuff, we have f of gx pointing down slope, f of k pointing up slope. So we would just take the difference in those two forces, okay? So I have f of gx minus f of k equals to ma, but a here I can just replace with r alpha. The relationship between a tangent and angular acceleration, again, is just by this factor r, coefficient r. So a is equal to r alpha. I can make that substitution. And then from here, I can break up mg sine theta into mg sine theta, or f of gx, excuse me, into mg sine theta. F fric I'll keep normal because that's what I'm trying to substitute out of this particular torque function. And then from here, hopefully you recognize that you need to solve for f fric because that's what you're trying to replace it. Okay. So to move f fric, negative f fric, I'll move it to the right side of the function. That'll make it positive. And then this mr square, I will move it to the left side, which makes it negative. So there you have it. and then you can just substitute. Okay, so instead of f fric in the next line, I'll carry it down. You can just replace it with mg sine theta minus mr alpha, which is what I have here in the screen. And then here, this r here, I just carried it down as part of my function. And again, the moment of inertia value is just 2 fifths mr squared. Don't use the parallax theorem in this particular approach, times alpha. And we can cancel one of these r's out. This r is outside of the parentheses. That's r. On the right side, there's r squared, so at least one of them will cancel out. Okay, so make sure you cancel r's where and when appropriate. Do not cancel this r inside this parentheses out, because that r is just to only to this term, why this term has no r. So make sure you don't do that. All right. Here, you notice that you have R alpha, you have R alpha, so combine like terms. So if you combine like terms, we can just move this negative R alpha to the right. That makes it a plus sign. Here we have 2 fifths R alpha, and this is R alpha, so common denominator is going to be a 5. All right, so this will be 2 over 5, and then this will be 5 over 5, because 5 over 5 reduced down to 1. And then 2 plus 5 is 7. Common denominator is 5. So this is where we have it. All right, so if you combine like terms, 2 plus 5 is 7, and then 5 is the common denominator here. And then to multiply both sides by 5, and then divide both sides by 7 just to find alpha. Okay, so and then the r here gets divided down. So if you do all that, we know g is 9.8, we know theta is 30 degrees, and then we know r is 0.3. If you plug that into your calculator, you should get the same value, and then from there, we just plug it back into there, and it will produce the same answer of 2.27 seconds. So the strategy, again, just teaches you how to use torque via different perspective. All right, so let's go ahead and do part C. Part C asks us to prove, that the linear acceleration, or ACM, is given by this particular function, 5 over 7 g sine theta. All right, so not too bad. So start with Newton's second law. All right, f of gx minus f of fric equals ma, and then f of gx can be broken down to mg sine theta minus f fric. Again, we're trying to find a, so I need to keep a in this particular statement. All right, but I don't know what f fric is. Okay, I don't know what f fric is, so I need to get rid of f fric. So the part here, same strategy here. I'll use this center of mass as my pivot, and then what's causing my torque is the force of friction, because it is a distance of r away from the pivot. So here, friction is what's going to cause the torque, and that's just the distance of r away from the center of mass, aka the pivot. I, in this case, is not shifted, so the moment of inertia for a solid sphere is just 2 fifths mr squared. And I'm going to go ahead and break up alpha equals a over r. Okay, so from the relationship, a is equal to r alpha. So to solve for alpha, it would just be a over r. All right, so here, this r is going to get moved down to the right side, which makes r squared, and then the r squared on the top and r squared on the bottom is going to cancel out. And so you do basic math there and cancel things properly. F fric is just 2 fifths ma. Okay, and then from here, we can just substitute it in. So instead of f fric in this line, we can substitute in 2 fifths ma. So you notice here you have an ma on the right side of the equal sign, you have an ma of the same term on the left side, but this is negative 2 fifths, so combine like terms. If you combine like terms, I'll go ahead and cancel out the m's there. You don't have to, but we can go and clean it up a little bit. But it still doesn't change the fact that this is 2 fifths a, and then that's an a. So combine the a's, and that'll give you this particular function here. Okay. So here's a, and there's 2 fifths a. So multiply this by 5, divided by 5, which is just 1. And then this is what I have here. Again, common denominator stuff. And then from here, we notice that we have the like terms. 5 plus 2 is 7. The common denominator is just 5. So it leaves us with g sine theta is equal to 7 over 5. Again, 5 plus 2 is 7. And then common denominator is 5. So we just carry that 5 down. But to solve for a, we just multiply both sides by the reciprocal of this fraction, which is 5 over 7 on both sides. And that'll leave us with this particular statement. Okay. All right. I hope that helps. And I hope you also recognize that in this particular problem, the mass of the solid sphere is not given to us. Why? Because it cancels out in a lot of these strategies. Okay. So as you can see, everything that we've done in part A, B, and C did not require mass. So it's important that you pay attention to what variables are dependent and independent on. All right. Other than that, I hope that helps a little bit. Stay nerdy. Don't be wild.